Welcome to Chapter 2. So motion in 2 dimensions. So Chapter 1 we did motion in straight lines. Now we will investigate motion moving in 2 dimensions or planar motion. So if you imagine the whiteboard in front of you, it can move around trapped within that whiteboard. That would be 2 dimensions. So let's have a quick look at some of the topics we're going to investigate. We've already done vectors and scalars. We're going to solve some vector problems involving distance and displacement. We're going to return to those, only we're going to have 2 dimensions. And we're going to describe total displacement and in 2 dimensions by scale diagrams and by the component method. And we're going to solve some problems related to horizontal and vertical components of motion, which we're going to call projectile motion. So we'll be launching things across the room and into the air. And yeah, so let's get started. So by the end of today, I should be able to calculate the displacement of an object in 2 dimensions using a vector scale diagram. Okay, so we're going to do some drawing today. You'll need a ruler and potentially a protractor. So quick review. I'm going to make this a tiny bit larger. Vectors. So a scalar is a quantity that can be described by a single number. It's just the magnitude. So our scalars so far are distance and displacement. Or sorry, it's just distance. The vector counterpart to that would be displacement. A vector is a quantity that has both direction and magnitude. So again, a scalar would be speed, our vector is velocity. So to represent a vector, we will use an arrow. And so the tail is where we start, or the initial point. The head is the pointy part, that's the end. Okay, so if we were to drag an arrow from A to B, going this direction, okay, that would be how we would define this vector. It's a vector AB. This is where you start. This is where you finish. Okay, the length of the vector represents the magnitude, and the way the arrow is drawn represents the direction. Okay, so magnitudes are always positive, and then the vectors are drawn to scale. So a larger arrow represents a larger magnitude. We talked about that already. So the direction part of this discussion, we will use compass directions for sure. So north, we should probably do a quick recap. North, east, south, and west. It's worth writing that down because lots of people make mistakes on that for some reason. We'll also use something called bearings, where we'll start at the north and we'll measure in a clockwise direction. And then we can even do something as simple as up, down, right, and left. Okay, so directions won't be complicated, they just have to be clear. So let's have a quick look. This is a polar coordinate system. So it's got angles on it. We're saying north at the top here is where our 0 is. As you can see over here, our positive direction is to rotate clockwise. For those of you who are unfamiliar with analog clocks, that's the kind that have hands that rotate, not digital. So as we rotate clockwise in this fashion, that is considered our positive motion. Okay, and you'll notice the values are typical circle values that are used. If you're a snowboarder, you'll know what pulling a 180 or a 360 and those types of things are. So what we want to look at is how we communicate some of these directions. So maybe I better make that a bit smaller. So let's look at this one. North 30 degrees east. Okay, so when you look at this, the north is where we start. The 30 degrees is how much we're going to turn, and the east is the direction we turn. So I'm going to start at north, turn 30 degrees. Okay, so that is this spot right here. So the direction for this vector would look like that. Okay. So now that's a really badly drawn vector. There, that's better. So now that's one way of describing it with compass directions. We can also describe this with bearings, and bearings are measured from north. Okay, so it would just be 30 degrees. So it would be 30 degrees. So if you just said the direction is 30 degrees, we would assume you're measuring from north and measuring in a clockwise direction, and we would turn to the right. Now if we have something like this, which is southwest, when you have this, this is the cardinal directions are north, east, south, and west. This is exactly halfway in between. You could have also written it this way. Most people don't, but just so you can see they're the same thing. So this is started south, turn 45 degrees to the west. So if we started south right here and we turn 45 degrees to the west, a little bit too far, should be somewhere in there, 225. Oh, the red line. I got to get to the red line. I think it's where it is. That looks about right. Okay, so there's my 45 degrees right in there. So then my vector would be going like that. Now the equivalent of south 45 degrees west, if we had to measure all the way from the north, we have to come all the way around. That would be 180 degrees plus 45, which would be 225 degrees. Okay, so those would be matched up. And then lastly, 300 degrees. If we start with a bearing, 300 degrees is right here. So now that would be turning all the way around. Now there are multiple ways to represent 300 degrees. Let me just cut some space here. We could say it's west 30 degrees to the north. So west 30 degrees to the north. That would be a possible answer. We could say it's north 60 degrees to the west. That would also be an acceptable answer. So again, we're starting. This is where we start. The first letter is where we start. The angle is how much we're going to turn. The second letter is in the direction we turn. Okay, so we'll get used to moving in between those two, but those are our fundamental sort of directions for displacements. All right, let's see if I can make this fit now. So drawing vectors. So I want to draw a displacement of 3 kilometers to the southwest. So we want to select the scale. So I've done that here. 1 centimeter is going to equal 1 kilometer. I want to select a convenient initial starting point. So I want to think about this problem and place my starting point on the page to leave me some room to draw. So this is my starting point right here. Use a protractor to mark the correct direction. So if I take my protractor here, and I don't want to use the edge of the protractor, I want to use the lines on the protractor. And that's why I draw these little X's for my starting locations. It makes it easier to line things up. Okay, now I want to turn to the southwest. Well, southwest, here's south, here's west, so exactly halfway in between would be right there. Okay, so once you've done that, I always find it really useful. I'm just going to move this guy out of the way. Whoops. Let's move that guy out of the way, and I'm going to put a dot right there. So now when I go to draw my actual vector, okay, so I have centimeters written here, and I'm going to try and draw 1 kilometer is, oh, don't change that, from there to there. Oh, it's pretty close. So let's go move it up. So my actual vector will start at the black dot and will go to 0. Okay, and that is my vector. Okay, so if I move that out of the way, the red dot was just there to help me with direction. Doesn't want to move, there it goes. So that vector that's in space there, this is 3 kilometers at southwest. Okay, so that's the strategy we'll use. It looks really simple. It takes a little bit of attention to detail. You need a sharp pencil. You need to start on the exact locations of the measurements. If you can learn it, it'll serve you well because it'll replace doing some calculations. So here we go. Here's our challenge. Use your ruler and protractor to draw 2 vector displacements. 8 kilometers to the south, followed by 6 kilometers to the east. So include the arrow directions. Make sure the diagram is as accurate as you can make it. Okay, so if you can do that, please. So pause the video, draw that. Make sure your pencil is sharp. Okay, once you have it drawn, measure the resultant displacement, so from start to finish. So I'll just make a doodle up in the corner here. So if we have south 8 followed by 6 to the east, the resultant displacement is going from start to finish. Okay, now if you've done this really well and you measure the angles, you should find that that resultant should be 10. Okay, and it should be not close, it should be a perfect 10 if you have done a really, really good job. Okay, if you want to go in and use SOHCAHTOA and find the angle, okay, you can measure that angle with your protractor, and then you can check it with your SOHCAHTOA. So if we looked at this, I'm just going to do a quick tan theta of 6 over 8. 6 divided by 8, shift tan equals, it should be pretty close to 37 degrees. Okay, so that's a quick test to see if your drawing skills are intact. Okay, so here's what mine looks like. I have 1, 2, 3, 4, 5, 6, 7, 8 down the left side. You can see I've measured right here. That's pretty close for the digital tool. Okay, if I can rotate it, remember how to rotate it. See if it'll let me. There we go. The bottom one is 6. So if I rotate, come on, rotate. There we are. You can see I'm pretty darn close to 10. Okay, so my measurements here are good. If I put my protractor on here, I should find I'm really close to 37. 37, there it is right there. Okay, so even using the computer, I've got a pretty accurate vector scale diagram. Okay, so equivalent or equal vectors. So you can see that AB is equal to CD. The little arrows on top is how we denote vectors. And remember, they go from the tail end all the way to the head. Okay, so tip to tail, tail to tip. I got to make sure I say that right. Two vectors are equal if they have the same magnitude and they are parallel or have the same direction. So we can say AB is equal to CD only if they are the exact same length, which they are, and they have the exact same direction. Okay, those are two vectors that are equal. Opposite vectors have the same magnitude but opposite direction. So you'll notice here's AB, okay, and if you look at this BA vector, okay, it's the same length, but it's going in the opposite direction. Okay, so AB would be equal to negative. That's incorrect. It should be equal to negative BA. Oh, sorry, these guys are matched up. My pictures dragged a little too close to each other. There we are. So these two would be the same. Okay, so adding vectors, and we're going to spend more time with this in the future. This is a big component of some of our advanced physics stuff. To add vectors, we arrange them tip to tail. So let's go grab our highlighter. So right there, that's tip to tail. So when we're adding vectors A and B, we want to place them tip to tail. The resultant, in this case, the resultant is C, and it is going from the very beginning of the problem to the very end of the problem in a straight line. Okay, so that is an important word to know, resultant. And if you come over here to the green box, you can see A plus B equals the vector C. It's a strange notation, we'll get used to it. Or if we looked at this, A plus B, and then if we minus C, we would get right back to where we started. So you could think of this as going down the negative of C. We would get right back to where we started, and that's where the 0 comes from. If we have a bunch of vectors, A plus B plus C plus D, the cool thing is we can add them all together, And E would be the resultant. It's going from the very beginning to the end in a straight line. And it doesn't care about all of the little vectors in between. It just goes from point A to point B, and it's quite content. Okay, that's a bit beyond what we're going to do, but just so you can see it. All right, so let's try some. So use the scale diagram to determine the sum of each pair of displacements. So delta D1, so 72 centimeters to the west, followed by 46 centimeters to the north. Okay, so I'm not going to be able to solve all of these on the board. So you have a 72 to the west and a 46 to the north. Okay, so again, you're going to draw these with detailed, accurate pictures. The next one, make sure we have our directions right. 65.3 meters east, 42 degrees to the north. So again, we'll start with a little x. I'm going to start to the east, and I'm going to turn 42 degrees to the north. Okay, so I'm turning that direction. Okay, this is for question B. And then you would follow that with 94.8 to the south. So there would be, again, a little x here, and then we would be going to the south. Okay, so if you want to pause the video there, follow the steps to draw your vectors, and then I'll erase the answers. You've got 2 questions there you can try. Okay, welcome back. So let's see how well you did. So for the first one, we should have 85 centimeters at approximately west 33 degrees to the north. So if you look here, west 33 degrees to the north. So my sketch was pretty close. Second one, 70.5 meters, and we should have east 46 degrees to the south. So if we start here and we go east 46 to the south, the 46 would be in there. Okay, and then lastly, we have a cyclist travels 450 meters west 35 degrees to the south. So let's just get rid of all of these guys for a second here. So we're starting at some location. We're going west, but we want to turn 35 degrees to the south. So there's my vector. This is the 35 degrees. And then rounds a corner and travels west 60. So again, I might put another little x there. West 60 degrees to the north. And there would be my 60. Okay, so this one here is 450. This is 630. So my resultant should be somewhere like that. Again, I'm just estimating. So let's take a look. We have 740 meters, so I have a longer vector, west 23 degrees to the north. So this red vector right in here, this angle in here would be 23 degrees. And if the whole motion takes 77 seconds, we're going to divide that displacement, the 740, by time. And you'll notice, though, they kept the direction. Because we found a velocity, we need that direction as well. Okay, on page 65, you'll find a couple more to try, 1, 2, 4, 7. And there is also a vector scale diagram task. Thanks for tuning in.